task to show, using the definition of the limit, that the limit as x tends to 3 of the function f of x equals 12 minus 2x is equal to 6. So my question for right now is, why is 6 the limit that we expect? What is it about 6 that makes this a high percentage guess for what the limit of this function is as x tends to 3? Yeah, Kenny.
Well, as x approaches 3 from the left and right, it will both go to the same number, which is 6.
Okay, but then where does that 6 come from, is my question, I guess. All right, so there's our clue, right? So you're right, that as x tends to 3 from the left and from the right, we're going to see that the value of f of x tends to 6, but that's something that we're going to prove. Before we prove it, we can expect 6, or we can guess 6, because it turns out that f of 3, if I ask for the value of this function at x equals 3, I get 12 minus 2 times 3 equals 6, right? But there's a big difference between the statement written up here in red, or I guess purple, the limit, and the statement written up here in green, right? In principle, those two things might have nothing to do with one another. The limit is sort of telling us the behavior of this function near x equals 3, whereas the value f of 3 tells me not about the nearby values of f of x, but this tells me what is the value of the function at x equals 3. And those two don't have to be telling the same story. They aren't necessarily telling the same story. But it turns out that in calculus you get used to this idea, right, that if I want to evaluate a limit, the first thing I should try is just stuffing this x value into my function and seeing what the value of the function is. But if those two are not always telling the same story, we won't always get away with that. Right? There are definitely functions that we can write down where if we just stuff the value, the x value that we're trying to take a limit, if we just try to stuff that value into the function, we're going to get an answer that might not be equal to the limit. We might get an answer, and yet the limit might not exist at all, or vice versa. The limit might exist, but the value at that point might not exist. So these are two independent questions, and today's pivot is going to be talking about that gray area, right? Why is it that we're able to make that leap in this problem and actually get a reasonable answer, but why might it not work in general? So taking one more quick look at this proof that we just wrote up. In order to prove that this limit was in fact equal to 6, we took the definition, so the definition of the limit of a function, which Kenny wrote down right here. This limit is L, 6. If for all epsilon greater than 0, we can find a delta greater than 0, such that whenever the distance between x and 3, in this case, is between 0 and delta, then it will be true that the distance between f of x, the y value, and L is less than epsilon. So doing some scratch work on this inequality, by substituting it for f of x, substituting it for L, and then trying to isolate, by the way, why was absolute value of x minus 3 the right thing for us to try to isolate in this scratch work? Why was that exactly what we wanted?
Because we want to take absolute value of x minus a, and a is like approaching 3.
Right, exactly. In this problem, the a, or the x naught, whichever version of the definition that you're using, that x value that we're approaching is the value 3. And so the quantity we're trying to isolate in our scratch work is the absolute value of x minus 3, because that's the distance between x and 3. So when we're doing our scratch work, we're trying to uncover an absolute value of x minus 3 in that process. And you find out that absolute value of f of x minus L is less than epsilon, exactly when the absolute value of x minus a is less than epsilon over 2. And then that's the definition that you use for delta, to find delta to be epsilon over 2. And then for any x, which is at a distance of between 0 and delta of the point 3, you can then show that the absolute value of f of x minus L is equal to 2 times the absolute value of x minus 3, which, by our assumption here, is less than 2 delta. And the definition of delta as being epsilon over 2 means that that makes that, therefore, less than epsilon, completing the proof. Now, here's my question. Where did this 2 over here come from? We can kind of see where it came from in the algebra. But my question right now is, what is it about this function that makes that 2 the right choice?
Does it have to do with the slope?
It might have to do with the slope. So that's going to be the case that I want to make for just a couple minutes here. Because what is the slope of the graph of this function f of x? Well, it's not quite 2. It's negative 2. But yeah, in absolute value, the slope is 2, and absolute value is powering this whole definition. So it seems like this choice of delta should be related to our epsilon via some feature that involves the slope of the graph. So here's a graph of the function f of x equals 12 minus 2x. Here's the x value 3, right here on the x-axis. The y value 6. The claim is that the limit as we approach x equals 3 of this function is equal to 6. And so the idea is that once we choose a value of epsilon, let's say I choose the value of 2 for my epsilon. So what we're doing then in the definition is making the claim that we can get within 2 units of the value 6. So in other words, we can make the y value of my function between 6 minus 2, 4, and 6 plus 2, 8. So we can get the y values to be within this strip. And we can do that by making the x values sufficiently close to 3. And my question is, how close to 3 do we need to be in order to make this happen? So take a look, you can kind of see the green shaded part of the graph as well as the green shaded part of the x-axis as I change my delta up and down. So if I choose a delta to be 1.5, that looks like it's too big of a delta because there are some x values here whose part of the graph lies outside of this purple strip, more than 2 units away from L equals 6. So 1.5 is too big of a delta. On the other hand, if I choose a small delta like 0.5, now the entire part of the graph, which has an x value within 0.5 of our a, which is 3 in this case, that entire part of the graph is in fact within the purple strip. So if epsilon is chosen to be 2 by the universe, then if we choose delta to be 0.5, we'll be good. Right? Because it will be true that for all x which are within 0.5 units of distance of 3, their f of x, their y values, are definitely within 2 units of the limit, 6. But 0.5 is somehow too small. I could make that bigger and still be within this strip. My question is, how big can I make it? What's the largest delta value that we can choose such that the entire graph for that interval of the x-axis stays within the purple strip? Anything I choose that's bigger than 1 is going to slop outside of the interval. Anything I choose that's less than 1, and I've got a little bit of space left over here. See, right? There's a couple of little values of x within this green interval that are, that could still have their y values within the purple strip. So the delta that I choose that's right on that edge is delta equals 1. And that's not a coincidence, because if I label those 2 points on this graph at which my graph crosses my purple strip, what would these 2 points be? So 3 minus 1 goes down to 2, and then I go 2 units up. This is going to be 2 comma 8. And if I do the same thing going in this direction, this is going to be 4 comma 4. But the idea is that the slope of this graph gives me exactly the relationship between the epsilon that tells me, well, this is really 2 epsilon, I guess now. Maybe let me rewind the tape. We'll do it the other way. Epsilon is this radius of my interval on the x-axis, right? If we look down here on the x-axis, here's 3. This is my a, or my x naught. And then here's 3 plus epsilon. Right? So that distance here is epsilon. Sorry, it's not epsilon. It's delta. About that. So that radius there is delta. And meanwhile, on the y-axis, between 6 and 6 minus epsilon, that distance there is epsilon. And so in this picture, we can see that the ratio of the largest delta that we can choose to the epsilon, which is chosen to us by the universe, the ratio of that epsilon to that delta is exactly the same thing as the rise over run on this graph, otherwise known as the slope of the graph. So that relationship between the epsilon the universe chooses and the delta that we produce in our proof is very often, secretly if nothing else, informed by the slope of the graph of this function. When that slope exists. One of the stories we're not quite going to get to this semester is when is it true that a function actually does have a well-defined slope? What functions are differentiable? We won't be able to quite get there. But for those functions which are differentiable, for which we can actually say what the slope is, either the slope of the entire graph in the case of a line, or if we happen to have an example of a graph which is not just a straight line graph, then that slope, which we're talking about as the relationship between epsilon and delta, might actually be a quantity that would be different from place to place. Right? On this graph, it looks like the slope that I might need is, let's see, the slope of 4 would be the relationship between the y values, the epsilons here, and the deltas that I get. So taking delta to be epsilon over 4 is probably the right choice for this point in my graph. But that if I slide over to a different point, let's see, I slide over here instead. Now it looks like I might have a little bit, for a given epsilon, I might be able to get away with more delta inside here than I did before. So here epsilon over 2 might be maybe a little bit less than epsilon over 2. Kind of hard to tell, because again, these things are supposed to be true for all epsilon. So as I zoom further in, I should get a better sense of that relationship. Again, these are the kinds of things that we tend to do in calculus a lot. When we think about slope, it's always this infinitesimal quantity that exists really close nearby a point. It's all limiting behavior. But the point is, for this curvy graph, the delta that I choose might be different from different places to different places on this graph, because the slope on this graph behaves differently from point to point. And the slope somehow is telling me how much I need to pull epsilon back by in order to get a delta, which is safe enough that every x within delta of A is going to have a y value within epsilon of L. But the slope, when it exists, informs that conversation.